Today, I want to tell you about a very important foundational idea for calculus, and that is finding a limit. Let's get started. The limit of a sequence is the value that that sequence seems to approach as n increases. And the symbol that we use for that is just the abbreviation LIM. As n approaches infinity of whatever our formula is, whatever our sequence is. So let's look at a couple different examples. This says the limit as n approaches infinity of 1 over n. And so what that means is I keep putting bigger and bigger numbers in for n. What happens to this limit? Why don't we do that a moment? Here is a table, and I just will put in bigger and bigger numbers for n and see what happens. Of course, if we put a 1 in, 1 over 1 is just 1. And so if we divide 1 by n and kind of drag this down, you can see that these numbers are, well, they're all decimals, and they kind of seem to be getting smaller. Why don't we jump ahead a bit and plug in something like 100 and see what values we get. So now we're getting really kind of small numbers. What if we jump to, say, 10,000? Okay, now these numbers are getting smaller yet, and so forth. And so as n gets bigger and bigger, this expression, 1 over n, seems to be getting closer and closer to 0. We say its limit is 0. Why don't we look at a different example? In this example, we have the limit as n approaches infinity of n plus 3 over 2n. And so once again, if we start to put in some big numbers, we can take a look at what this formula becomes. First couple numbers, 2, 1.2, 1, and so forth. And then I'm getting into some strange decimals. Why don't we jump ahead to, what if we put in 100 and see now these numbers seem to be settling in on 0.514. Oh, nope, that's lower yet. If we jump even bigger to maybe 10,000, all right, these numbers look like they're 0.500. I wouldn't be surprised if, as we keep going, these numbers settle in on 0.5 or 1/2. So we would say its limit is 1/2. Now, there's a little bit more direct approach to finding limits than simply looking at a table like that. And so we'll be able to confirm that it really is 1/2 in a little bit. But that's the idea behind a limit. We say that if a limit exists, that the sequence converges. And so you might hear that word quite a bit. There's no promise that sequences will converge. So here's an example of a limit as n factorial over 3 to the n as n goes to infinity. If we take a look at that, by the way, to type this expression in, I had to use, can you see it? Yeah, factorial, F-A-C-T, parentheses. So let's see what happens to this guy. The first couple terms seem to get smaller, but then it gets bigger and then bigger yet. And then now I'm at 2 and 6 and 18 and 225. If I jump to 100, these numbers aren't displaying properly. They are so big. I'm surprised they're displaying it all without errors. I still don't have them all in here. Yeah, anyway, these numbers get bigger and bigger and bigger and bigger. And we would say here that the limit is undefined. Some people might say that the limit here is positive infinity. There's good reason to do that too, but it does not converge to a number. Now, how can you find limits? Here are a couple strategies. We basically did the evaluate. We plugged in big numbers for n and looked at what happened. And sometimes that's good enough and easy enough to do. Other times that may not work, or we don't have a spreadsheet handy, and so you might choose to multiply the top and bottom of the fraction by the same thing, and that's a really useful tool we'll see multiple times in our examples today. And there are also lots of theorems that you'll have to study eventually if you get into this in more detail that allow us to break limits up into smaller pieces and evaluate them that way. So first, maybe more challenging example here. What is the limit as n approaches infinity of 7n squared plus 2 over 2n squared plus 3n? If we just do the table technique, I have typed this one in ahead of time. Um, as I put in bigger and bigger numbers, you see these numbers are growing, but it's really hard to look at these decimals and kind of know what's going on. If we jump ahead to maybe the 100th number, put in 100, these numbers are still growing, a little slower, but I still don't know exactly what it goes to. Maybe 3.5. What if I go big time, 10, a million even? So yeah, I wouldn't be surprised if it's 3.5. But there's always this question of like, how big of a number should I put in? What's big enough? And so we're going to try a different strategy. Instead of evaluating things, I'm going to choose to multiply the top and bottom by something to clean this up. I've enlisted a handwriting expert to help me with this.
So, to find the limit as n approaches infinity of 7n squared plus 2 over 2n squared plus 3n, first thing I will notice is that the highest power of n I see anywhere is n squared. And so I'm going to suggest that we multiply the top and bottom of this fraction by 1 over n squared. This is not going to change the limit because you can always multiply a fraction by the same thing on top and bottom. And what this will do is we'll produce the limit as n approaches infinity. And on top, 7n squared times 1 over n squared, you're effectively dividing by n squared. And so that would become 7. And 2 divided by n squared would become 2 over n squared. On the bottom, 2n squared divided by n squared would become 2. And 3n divided by n squared would become 3 over n. Now that probably looks really sloppy compared to what we had originally, but now we can think about what happens as n gets really big. As n becomes a bigger and bigger number, 2 divided by n squared becomes 2 divided by 1,000, 2 divided by a million, 2 divided by a billion, 2 divided by something really big. This chunk is 0. So as we take the limit, this part becomes 0. This part doesn't change because it doesn't have an n in it. And so as we take the limit, the top becomes 7. On the bottom, 3 divided by n, again, as n becomes a bigger and bigger number, 3 divided by something big becomes 0. And 2 doesn't change because it doesn't have an n in it. And so the bottom becomes 2. And so our final answer then is 7/2.
So that strategy we can use in multiple other examples. And so let's see another one. N cubed over 3 plus 5n minus 2n cubed.
In this example, we're taking the limit as n approaches infinity of n cubed over 3 plus 5n minus 2n cubed. And again, first thing I see is that the highest power is n cubed, and so I'm going to divide everything by n cubed. If I do that, now I've got the limit as n approaches infinity of, on top, just a 1. And on the bottom, I've got 3 over n cubed plus 5 over n squared minus 2. And if I now take the limit by putting in bigger and bigger numbers for n and seeing what happens to each term, the top's not going to change. The bottom, if n is a big number, 3 over something big becomes 0. Over here, 5 over something big becomes 0. And this part isn't going to change because it doesn't have an n in it. And so it'll be negative 2. And so the final answer here is negative 1/2.
In this next example, we could just take the limit right now. If we put in a big enough number for n, the top is just going to be 5. And the bottom will get bigger and bigger and bigger depending on what n we choose. And so if we take 5 and divide it by something big, it's going to become 0. And so this middle example, its limit is simply 0. If you want to find the limit to the last one, I suggest you hit pause a moment and see what you could do. This is one where I think you should probably divide. Hopefully you thought to divide both top and bottom by n, and if you did that, you'd have 4 over n plus 1, and on the bottom, you'd have 5n over n, which is just a 5. And once you take the limit there, then the top will become 0 plus 1. And the bottom, when you put in a big number, that would just become 5, because the n over n cancels out. And so you've got 1 over 5, or 1/5. Let's take a look at a slightly harder problem.
All right, to find this limit, as 3 to the n plus 2 divides by 2n to the n minus 5, I might suggest dividing by 2 to the n. If we divide everything by 2 to the n, we will get the limit as n approaches infinity of, on top, 3 to the n over 2 to the n plus 2 over 2 to the n. On the bottom, 2 to the n over 2 to the n on purpose becomes just 1, and we'll subtract 5 over 2 to the n. And now I can take the limit. On the top, 3 to the n over 2 to the n, I'm not sure what happens to that as n gets really big. But here, if n gets really, really big, 2 to the n gets really, really, really big, and so 2 divided by 2 to the n is going to become nothing. On the bottom, 1's not going to change because it's got no n in it. Over here, 2 to some big number is going to be really big, and 5 divided by something really big will become 0. And so if I clean this up a bit, I've got now the limit as n approaches infinity of 3 to the n over 2 to the n plus nothing, and on the bottom just 1. And so if I clean this a little bit up, that's the limit as n approaches infinity of 3 to the n over 2 to the n. And if I use some exponent properties, we can say that that is the same thing as the limit as n approaches infinity of 3/2 to the n, which is the same thing as 1 1/2. And I can see here, if I plug in bigger and bigger numbers here, I'm just going to continue to get bigger and bigger numbers. This is just an exponential function that's going to grow and grow and grow and grow. And so this particular limit does not have a limit. It does not exist. It's undefined.
All right. One last example. We're going to try to take the limit as n approaches infinity of square root of n squared plus 5 over n minus 5. This will require a clever little multiplication, and so if you want to give it a go ahead and try. Otherwise, you can watch and see what I did.
All right. In our last problem here, we've got the limit as n approaches infinity of the square root of n squared plus 5 over n minus 5. So in this particular problem, I am going to choose to multiply the top and bottom by the square root of 1 over n squared. So on top, the square root of 1 over n squared, and on the bottom, I'm going to multiply by the square root of 1 over n squared, but I'm going to take the square root of the top and the bottom and clean it up a little bit. So square root of 1 is just 1, and the square root of n squared is n. So even though it doesn't look like I'm multiplying the same thing on top and bottom, I am, because 1 over n and square root of 1 over n squared are the same. On the top, then, I can distribute this 1 over n squared to each of these terms, and that's going to still be under the square root, and I haven't taken the limit yet. This will become n squared times 1 over n squared, which is just that, plus 5 over n squared. On the bottom, when I distribute, n times 1 over n becomes n over n, and 5 over n. And I can clean this up a little bit more. This is now the limit as n approaches infinity. On top, I've got 1, all under square root, 1 plus 5 over n squared. And on the bottom, I've got 1 minus 5 over n. And so if I plug in a big number for n, say 1,000,000 or 1,000,000,000, this part becomes nothing, and the 1 part doesn't change. So on top, I've got the square root of 1. On the bottom, if I plug in something big, 5 divided by something big becomes 0, and so I've got 1 minus 0 is just 1. And so on top, I've got root 1, which is 1, over 1, and so the limit here would be a 1.
All right, so there are a couple examples of finding some limits. I hope you're able to try that on your own. Let me know if you have any questions, and I'll catch you in the next video.